So, electric potential and electric potential energy. They're related, but you need to distinguish the two very carefully. Here's the relationship that you have an electric potential at some point in space, and you have that electric potential because there are other charges around there. Any charge is going to produce electric potential in the space around it, just like it produces electric field in the space around it. Then some new charge comes into the picture to interact with the potential that was created by the charges that were already there. And now you've got some, as a result, you have some electric potential energy that you did not have before. So just say that again in a little bit more detail. Change in anything is just the final value minus the initial value. So the final electric potential energy is just charge times potential at the final location where this charge ends up, minus the initial potential energy, which is just charge times the potential at the starting point where charge Q started out. And of course, if you factor out the Q here, then you've got Q times the difference between final and initial potential. So to write that a little bit more compactly, change in potential energy is just the same as charge times change in potential. So let's imagine a little bit more specific situation. Got a bunch of charges here, and so they create in the space around them electric field and electric potential. So there is electric potential at that point and every other point in this neighborhood. Then some new charge, something other than the charges that were already here, comes into the picture, comes from far away, and lands at point X. So in this case, the change in potential that the charge Q saw as it moved from some point far away to point X is just this final potential at the final destination minus potential at the initial location far, far away. Well, often we assume that far, far away is so far away from all of these charges that they really don't influence the faraway point hardly at all. And as a result, we just say that the faraway point has a potential of 0, like too far away for these charges to have any influence at that faraway point. By influence, I mean create a field and a potential at that faraway point. So if that's now 0, then when the new charge comes into this neighborhood, lands at point X, it then interacts with the potential at point X, and as a result, you have an additional amount of potential energy that you did not have before. There was already some potential energy in the system here because of all the these charges interacting with each other, but now you've got some extra potential energy on top of all that when a new charge comes into the picture and interacts with the potential at this point. So let's look at a slightly more specific example. Let's say you've got a charged particle free to move back and forth along a straight line, and then there are other charged particles around there that create a potential, electric potential at points along that straight line. And the value of the potential is different at different points along that straight line. And here's a graph of potential versus location on that line. Potential in volts, and then location in centimeters. 1, 2, 3, 4, 5 centimeter marks. Okay, and let's say, in this case, the charge that's free to move around along that line is a charge of 0.1 coulombs. Just keep the numbers simple here. And we're also saying that whatever charges are responsible for creating this potential are already there. They create different values of potential at different points along the line. And then when charge Q enters the picture, comes into that neighborhood, it now interacts with those potentials that were already there, and you get potential energy that you didn't have before. So again, there's our relationship. And so this relationship tells us how much potential energy the system had when you put this charge at different locations, because the different locations will have different values of potential. So let's say we've got our charge moving in the positive direction. We give it a little kick so that it starts moving in the positive direction. A very quick kick, so that as a result, it hasn't moved very much during the time of that quick impulse, but it's long enough to do a little bit of work on the particle and give it a little bit of kinetic energy that it didn't have before. So we say that when at x equals 0, when it starts out moving to the right, it has a little bit of kinetic energy, and that kinetic energy we'll say is just 1 joule. All right, well, the system has potential energy at that point too, which is just potential at that point times the charge. The potential at that point is 40 volts, and then 40 volts times a charge of 0.1 gives us 4 joules for the potential energy. So then the total energy of the system, just kinetic plus potential, is 5 joules. So we gave it a kick and it starts moving to the right, and then after a little while it's now at the 1 centimeter mark, and things are a little bit different. At the 1 centimeter mark, let's start with potential energy in this case. Potential energy is still potential times charge, and at the 1 centimeter mark, potential is 30 volts. So 30 volts of potential times 0.1 for the charge gives us 3 joules for the potential energy. For simplicity, we usually consider these systems to be isolated systems, that is, no work done by external forces, and work done by external forces is the only way to change the system's energy. So if there is no work done by external forces, there is no change in the system's energy. The system's energy stays constant. So other things might be changing, but the total energy of the system isn't. So when the charged particle is at this point, x equal 1, the total energy is the same as it was at x equals 0. 5 joules. So, since this total energy is just potential plus kinetic, kinetic has to be 2 joules. 3 joules of potential energy plus 2 joules of kinetic energy gives us 5 joules of total energy. Okay. And let's keep going here. Let's say jump to the 4 centimeter mark. Well, the energy is staying constant, so we know that when our charged particle is at the x equal 4 centimeter mark, the system's energy is the same as it always was, 5 joules. But now, the potential energy is, as always, charge times potential, but at the 4 centimeter mark, the potential is 0. So charge times 0 potential gives us 0 for the potential energy. But it's still the case that potential energy plus kinetic energy gives us total energy, so that means the kinetic energy has to be 5 joules. Remember, at x equals 0, the kinetic energy was 1 joule. When the particle moved here, the kinetic energy was 2 joules. Now when it's here, the kinetic energy is 5 joules. Kinetic energy is increasing, which corresponds to the particle speeding up. Let's look at this last point, x equal 5. Total energy is still the same. Now, what's the potential energy? Same rule as always. Potential energy is charge times potential. At x equal 5, the potential is, according to this graph, minus 10 volts. So the potential energy is minus 10 volts times 0.1 for the charge. So the potential energy is now minus 1. Minus 1 joule. Right? Because potential energy is charge times voltage, and charges can be either positive or negative, and voltages can be either positive or negative. You're going to get a negative voltage created by negative charges. Then this can be either positive or negative. But anyway, it's still the case that kinetic energy plus potential energy has to equal 5. So in this case, the kinetic energy has to be 6 joules. 6 joules plus negative 1 joule gives us 5 joules for the total energy. So what was going on here? That kinetic energy increased as our charged particle moved from 0 to 5 centimeters. Kinetic energy increase, so it was a positive change in kinetic energy, and since kinetic energy is 1/2 mass speed squared, in order for kinetic energy to increase, speed had to increase. Right, the particle, as it moved in the positive direction, was speeding up. I'll go back to Physics 2201. Got something moving in the positive direction, positive velocity, and it's speeding up. You know that whenever that's happening, it happens because the net force points the same direction as the velocity. You're moving in some direction and there's something pushing you in that direction, you must speed up. This net force is going to, in this particular case, the net force is is an electric force from all the other charges that were there in the first place, all the other charges that create potential and create electric field. Since we're talking about force, it's the interaction between the charge and the field that creates the electric force. And this was a positively charged particle, plus 0.1 coulombs for its value. And what do we know about the direction of electric fields? The direction of the electric field is the same as the direction of the force on a positive charge. Well, we've got a positive charge and it feels a force to the right, so electric field is in the same direction as that. That is, the particles that were already there created electric field in the space around them, as well as creating potential, and then the charged particle interacts with that electric field in order to feel a force. Since it's a positive charge, the force it feels is in the same direction as the field itself. The field is pointing in the positive direction. Note one other thing here. If you move in the positive direction, you're moving in the direction of decreasing potential. So the electric field pointing positive, the positive direction is the direction of decreasing field, or to put it another way, the electric field points towards decreasing potential, points from higher towards lower potential. That's not just something that happens in this particular case. That's an example of something that happens always. Wherever there is an electric field, it always points from higher toward lower potential. For example, in just a really simple electrical circuit, let's say a battery that's connected to a light bulb. So here's the battery, and the positive and negative poles, and then here's a wire connected to the light bulb. And the light bulb is illuminated, and then the other wire that connects to the other pole of the battery. These 2 points here, at 2 different points along the battery, represent 2 different potentials. The plus sign and minus sign mean that the potential here is higher than it is here. So within all this wiring, if you move this way, you're moving from higher towards lower potential. So going through this circuit clockwise, you're moving from higher towards lower potential. Electric field always points in the direction from higher towards lower potential. So electric field will be always pointing in the clockwise direction. That means any charged particle that's positive would feel a force in the same direction as the electric field and get pushed this way through the circuit. And then anything with a negative charge, like an electron, would feel a force in the opposite direction, because that's what it means to be negatively charged. You feel a force in the opposite direction from what a positive charge would feel. So if the electric field points this way, negatively charged things like electrons feel a force pushing them this way, and it's actually the negatively charged electrons that constitute the current in an ordinary wiring. And they're able to make current because they're pushed this way, because there's an electric field that they interact with, and there's an electric field there because you created a potential difference. If electric field points from higher towards lower potential, it's pointing from one value of potential to a different value of potential. So you have to have different potentials at different places to get electric field. All right, let's look at one more example, thinking about energy and potential energy. Let's think about an electron. A negatively charged particle, and the charge is, to be specific, negative 1.6 times 10 to the minus 19 coulombs. And the mass, really tiny, is 9.11 times 10 to the minus 31 kilograms. And let's say that the electron moves, starts out here, and then just moves to some final location. And it's got some initial velocity here and some final velocity here. And let's say that the initial velocity is 2.0 times 10 to the 6th meters per second. And the final velocity we don't know. We're going to figure that out. And this electron is moving through a region of space that has other charges nearby. Those other charges nearby create potential at this point and at this point. And we'll say that the potential right here, potential at the initial location is 10 volts, and the potential right here, potential at the final location is 8 volts. So the potential change that the electron feels in moving from the initial to the final location is just final minus initial, and that's 8 minus 10, or minus 2 volts. Okay, we want to calculate the velocity. We're given information about how the potential changes, and of course that tells us how the potential energy changes. Right, we know this. So we can use the fact that the total energy of the system stays constant, and that means that if one kind of energy changes, another kind of energy has to change just as much, but in the opposite sense, in order to keep the total energy constant. Right, remember, whenever there is a change in the total energy, it could come from some change in kinetic energy or some change in potential energy. But in this case, if there is no change in the total energy, then this is 0. And so what we have then is that the change in kinetic energy is just equal to -1 times the change in potential energy. And since we know the charge, and we know how much potential change, we can easily figure out what the change in potential energy is. That will immediately tell us what the change in kinetic energy is. And since we know the mass and the initial speed, that's enough to figure out what the final speed is. So let's see what that looks like. Let's just write this out in complete detail first. Change in kinetic energy equals -1 times change in electrical potential energy. Well, change in anything is final value minus initial value. Final kinetic energy is 1/2 mass final speed squared, and then minus initial kinetic energy, 1/2 mass initial speed squared, and that's equal to -1 times change in potential energy, which is again final minus initial. And we know that change in potential energy is just charge times change in potential. So write it as -1 times the charge times the change in potential. Well, let's just calculate the value of the left-hand side here. -1 times the charge, which is minus. Don't forget the minus signs. They matter. 1.6 times 10 to the minus 19 coulombs times the change in potential, which is a decrease of 2 volts. The change in potential, as we saw a minute ago, was -2 volts. Okay, so negative sign times negative sign just gives us positive, and then another negative sign gives us a negative number for the final result here. So it's negative 1.6 times 2, or negative 3.2 times 10 to the minus 19 coulombs times volts. Turns out that coulombs times volts simply gives you joules of energy. Right? Because remember, volts, what is a voltage, or what is a potential in the first place? It tells you how many joules of energy you get when you put 1 coulomb of charge at that point. Tells you the number of joules of energy that you get per coulomb that you put at that point. So if this is the same as joules per coulomb, multiplying it by coulombs just gives us joules. Okay, and then that's equal to all this. Let's factor out the 1/2 m. 1/2 m, V final squared minus V initial squared equals that. And put in the numbers, 1/2, 9.11 times 10 to the minus 19 kilograms equals, or times, V final squared, which is what we're trying to figure out, minus V initial squared. Remember, V initial was the initial was 2 times 10 to the 6th meters per second. So the initial squared is just that squared times that squared, which gives us 4 times 10 to the 12th. It's a squared velocity, so it's really meters squared times seconds squared. And all that is equal to this, minus 3.2 times 10 to the minus 19. Okay, and this is the kind of situation where uh, you, in one sense, you know what to do. You've done it a million times before, but since you're thinking of trying to think of so many other things simultaneously, uh, you might end up making a mistake anyway, even if you know better. That is, making an algebra mistake. We're trying to solve for that, so the first thing we have to do is get rid of all multiplying factors on the left-hand side. That is, we divide both sides of the equation by that. So that now the left-hand side is just v final squared minus v initial squared. So do that. And now all we have on the left-hand side is v final squared minus v initial squared, which is 4.0 times 10 to the 12th meters squared per second squared, and that's equal to this divided by all this, or minus 3.2 times 10 to the minus 19 over 19 joules over 9.11 times 10 to the minus 31 kilograms time this mass times 1/2. When you have a 1/2 in the denominator, that's the same as having a 2 in the numerator. But anyway, that's what we've got. Let's just rewrite that a little bit by solve that equation for v final squared. Just get v final squared all alone on one side of the equation. You do that by adding 4 times 10 to the 12th to both sides of the equation. So what we come up with looks like this. V final squared, that's all we have left on the left side of the equation because we added 4 times 10 to the 12th to the left side. And then on the right side we added 4 times 10 to the 12th to both sides of the equation. Minus 3.2 times 10 to the minus 19 joules over 9.11 times 10 to the minus 31 kilograms, and then a 1/2 in the denominator is the same as 2 in the numerator, so I'll write it like that. And look what happens here. You're subtracting something from the initial velocity, which means the final velocity is smaller than the initial velocity. The electron was slowing down. When you do the numbers here, you find that the final velocity actually comes out to, let's see, about 1.8 times 10 to the 6th meters per second. And then remember the initial velocity was 2 meters per second. So the electron was slowing down. Let's see how that relates to some other things we know about field and potential. So the electron is moving this way. Here's its initial location. Here's its final location. And the initial voltage was 10 volts. The final potential was 8 volts. So moving this way, you're moving towards decreasing potential. Here it's higher, 10. Here it's lower, 8. What did I just say a few minutes ago? Electric field always points from higher towards lower potential. So if this is higher and this is lower potential, electric field must point from left to right. The electron is a negatively charged particle, so it's going to feel a force in a direction opposite to the direction that a positive charge would feel. Well, the electric field points in the direction of the force on a positive charge. So if we were talking about a positive charge, it would feel a force that way. But we're talking about a negative charge, so it feels a force in the opposite direction. And as we remember from Physics 2201, whenever you have a force pushing backwards on you, a force that points opposite to your direction of motion, you must slow down. Right? Those kinds of opposite directions for velocity and force will always result in the thing slowing down. And of course, slow down is exactly what we saw. Right? The initial velocity was 2, and the final velocity was 1.8 times 10 to the 6. All right, now it's your turn to try some things in the assignment.